All right, let's take a look at this clicker question here. So the correct answer is this one right there. And let's think about why that is correct. First of all, we know that the sign on each one needs to be opposite. That's because for every mole of N2 that is consumed, some NH3, ammonia, is produced. So therefore, the rates are going to be opposite of each other. So that leaves us with this option or this option, because those are the only two ones that have opposite signs. Now, this is the tricky bit. Is it a 2 in front or a 1/2 in front? Okay, so here's the way that I would think about it. For every 1 mole of N2 that is being consumed, 2 moles of NH3 are being consumed. Therefore, the rate of NH3 production is twice as much as N2 consumption. Therefore, we would have to multiply times -1/2 in order for those two rates to be the same number. So that's why this one is the correct answer. The next section of chapter 18 talks about potential energy surfaces. And these are abstractions whose usefulness cannot be overemphasized. If you can find a way to visualize what they're talking about in terms of a potential energy surface, or you'll hear me say a potential energy landscape, it helps your intuition about these things so much. So I want to help explain what these surfaces mean, where they come from. The first and most important thing to note is that the altitude of a given point on the surface is going to be an energy. And in this case, it's potential energy, though there may be other kinds of energy surfaces. Like, for instance, there might be a free energy surface or something like that. So if that axis is energy, then what do these other axes represent? Those can represent any number of things. They might be the distance between two atoms. They might be the angle between 3 atoms. They might be the different conformations of a molecule. Like one example we'll see very soon, if we have 3 atoms and they're all separated apart from one another by a certain distance, then we might be able to call this one R1 and this one R2, and those might be the 2 variables that are describing this surface. Now, when it comes to molecules, most of the time, the potential energy surfaces are very, very bumpy. And that's what's indicated with this picture over here. And in a moment, we'll talk about protein folding and how the folding of a protein can be understood as a system moving along or exploring the surface of a high-dimensional landscape. So this slide talks briefly about how in my postdoc, which was after I got my PhD, I worked on the protein folding problem. And it is a very interesting problem to me. So you're probably familiar with the process of a protein folding. It goes from a very disordered arrangement to a much more highly ordered arrangement with secondary structure elements, disulfide bridges, interactions of that sort. And one way to understand this is that when the protein is unfolded, it is existing somewhere high in altitude on a potential energy landscape. And then as the protein adopts different folds, it's sort of like it is exploring around the valleys and the saddle points and the mountains of this landscape until it finally reaches the lowest point on the landscape, and that is the folded conformation of the protein. And you may know that this is a famously difficult problem. Given a primary sequence of the primary amino acid sequence of a protein, can its final fold be predicted? And one of the most useful ways of understanding this problem is through potential energy landscapes. So here is an example given by the book where a potential energy landscape can help us understand a chemical reaction that is occurring. All right, so let me explain the situation. We've got a complex or a molecule AB, and then it's reacting with C, and then there's some sort of equilibrium with A being bumped free, and then the complex BC being formed from that. Okay, so let's think about these atoms graphically. We've got atom A, and it's bonded to atom B, and then C is somewhere out over here. Then you probably know from your studies in chemistry so far that when the C comes and moves in, then it's going to encounter the B, and it's going to begin to push the A out. And so I'm going to draw dotted lines to represent bonds that are either forming or unforming. And then eventually the C kicks the A out, and the A just floats away. So there's the procedure that happens during the reaction. This step right here is called the transition state. And it has a higher energy than either of these two situations right here. So this is just depicted by another one of these reaction coordinate sort of little landscapes here where we've got energy on this axis and the reactants are over here, and then we have a barrier and then the products over there. So there's the products, there's the reactants. This is exactly what's happening in this situation. So the transition state has a relatively high energy, and often the quantities that are described in the transition state are indicated with the following symbol. That's a double dagger. You'll often see that symbol associated with the transition state. Okay, so if we were to represent the distance between atoms A and B, we could call it RAB. And then the distance between B and C would be RBC. By the way, we are neglecting the possibility that C could come in from some other angle. We're assuming that C is coming straight in at 180 degrees to the bond between A and B. So now we could, for any given distance RAB and RBC, plot the landscape, the energy on a landscape, okay? And because there's going to be different energies for each of these different distances, it's going to become a surface, and we can make sort of a topographical representation of that surface here, or we could actually make a three-dimensional plot. Now, this entire process of this reaction occurring is equivalent to the system kind of working its way up this valley, and then it crosses this landscape and then goes out to the products over there like that. Notice that the distance RAB is getting pretty large, and then RBC stays relatively small after the transition state is crossed. So let's think about a couple other places on the landscape. Right here at that spot on the landscape, that would be like RBC and RAB having very high values. So that would be like A, B, and C all existing at very far distances away from each other. But over here at this spot on the landscape, they're all very close. And that would be like A being bonded to B, being bonded to C, all at the same time. And that's also energetically unfavorable, so that's high up on that energy landscape.